Codemotion.
Hello everybody and welcome to my presentation on Infinispan, the open source data grid platform. Before moving forward, let me introduce myself. My name is Mircea Markus. I've been working for Red Hat for the last 6 years, mainly involved in the clustering stack. Projects such as JBoss Cache, JGroups, Pojo Cache. Starting with 2009, I've been involved in Infinispan. I'm one of the founders of the Infinispan project, which I currently lead. You can find me on Twitter at Infinispan or at my name, or on the Infinispan blogspot, Infinispan blog, which is hosted on Blogspot. These are the topics I'll cover in this presentation. I'll start by talking a bit on what Infinispan is and the way it organizes the data. Then I'll briefly discuss some API concerns before moving over to some more advanced features it has, such as transactions and persistence, querying as well. Then there's the main section of the presentation in which I'll cover 4 of the use cases, the 4 core use cases Infinispan can be used for. And the presentation ends by enumerating the main features which are currently being added to the Infinispan project and which will be released soon. So let's start with the beginning. What is Infinispan? Well, it's a data storage engine composed of a set of processes that communicate with each other over a network, over sockets. In clustering terms, or in Infinispan terms at least, each such process is called a node and has some memory available for storing data. If one of these processes goes down, the data which is kept in its memory, we normally replicate that. We keep several copies of the same data just to protect ourselves for such process failures, which are to be expected. It is also elastic. It is built with the idea that processes will fail and nodes will go down and machines will go down. So it accommodates easily such failures in the sense that users won't be affected. So the users that are connected with the storage will still be able to work with the storage, and there will be a minimal impact in the performance of the user access. It is open source. It is LGPL 2.1. Well, that means that both the code and the binaries are available for you to use free of charge. The plan is in future to move it to an even more liberal license, the Apache license. But all these aspects will be discussed in more details in the next slides. So Infinispan is a data storage, not a monolithical memory block. It's a distributed data storage. It's basically the total capacity of storage is equal with the sum of each of its node storage capacity. Each such process is started on a machine, and they connect to each other over the network, and they form a cluster. For the network communication and this discovery of nodes and finding each other, all this functionality is provided by JGroups, which is a reliable multicast library which has been around for about 10 years now. It's quite used, and is developed again in the JBoss community. So from a client's perspective, Infinispan, if you look up, Infinispan can be accessed either from the same process, so the client and the storage would be located in the same process, or we supply various remote access protocols. It can be used as a memcached, server. Hot rod is an internal protocol we developed. I'll discuss a bit more about it in the next slides. Also REST, you can have a REST API, so access it through whatever REST client, well, not a client, just HTTP. On top of the storage engine, which is basically RAM, but you can also overflow the data to disk. We built some services such as transactions. We support X8 transactions, distributed transactions, querying, multiple flavors of querying. We also provide MapReduce tasks, so you can execute MapReduce tasks in parallel over the whole cluster. And very important, monitoring, because being a distributed system, there are many things to take to look at, and you do want to have a centralized console to which to look and just know the state of your system. So the Infinispan cluster is highly available. That is, if a node goes down, the clients that are connected to the cluster will still be able to operate, and there won't be a stop the world. So there won't be 2 seconds in which we just block. We will continue provide access for the connected clients. So well, memory by its nature is volatile. So how can we be highly available, and more importantly, how can we make sure that we won't lose your data when a node goes down? In order to protect against this scenario, nodes going down, which will happen and do happen, basically we replicate the data you place in the in-memory grid. We support two modes of replication. The total replication, in which whatever you put in or whatever you write in one node gets replicated to all other nodes in the grid. That gives a very high or very high protection against nodes going down, but also your storage capacity is limited to the capacity of an individual node, so everything gets copied around. That can be useful if you have, for example, only metadata. You don't have that many information, don't have that many data to store. The advantage of replicated mode is that whatever node you read from, you have the guarantee that data will be placed in that node. So the read speed is very high. The write speed is a bit slower, because whatever you write somewhere gets copied around. But if you have a lot of reads, not that many writes, and not a lot of data placed in the grid, replicated mode would do, or for smaller clusters as well, up to 4 nodes, for example. We found that it can be a good balance. We also support partial replication, which we call distribution. It's based on consistent hashing. Basically, you define the number of replicas for the data you place in grid. By default, the number of owners is 2. So that means that as long as you have a single node failures, you are guaranteed to have the data copied on at least one more node. So if you need more resiliency to failure, you increase the number of owners. But normally 2 is a good enough balance. Again, topology changes will happen. Some planned. You'll just take some nodes down. But the worst ones are when node or multiple nodes crash. And in order, for example, to preserve the number of owners, what we'll do, we'll shuffle state around. So if a node dies and a piece of data, and you have, for example, number of owners set to 2, so it's just one more node that owns that data. What we will do internally, we will just take the data from that node and copy it somewhere else, so that we preserve this number of owner invariant. Elasticity is another very important aspect when it comes to in-memory data grids. So one of the core architectural principle we built Infinispan on is that nodes would be frequently added and removed from the cluster. Either because, frequently added because in today's world, in the cloud in particular, your storage capacity might grow and shrink based on the user demand, and it's more frequent than before the clouds became mainstream. So it's very suited for cloud storage as well. Again, when it comes to unexpected crashes, there are two very important aspects to be considered. The most important one being that no data is being lost. We will preserve your data. And there's no stop the world. So users connected, and that's kind of hard to achieve if you think about it, because there is data being written and it's being shifted around all the time. So if you take a node down, you know, not to stop the cluster and still offer very high consistency guarantees is quite hard. So we use some quite sharp algorithms behind the scene to make sure that if a node or multiple nodes go down, there won't be a stop the world. We won't just block all the clients for a while and then let them go. API-wise, Infinispan is primarily a key value store. So it can basically be accessed as a consistent hash map. It literally, so the Infinispan implementation, it literally extends the Java util concurrent hash map interface. There is a standardization effort for caching libraries, JSR 107. We are very involved in that. Actually, the first, well, this standard is it has been around for quite some while, for quite some time, 10 years now. Hopefully, there will be a release to be included in Java EE 8. There are draft implementations of this, or draft releases of this protocol, of this standard. And we, in Infinispan, even now implements the JSR 107 interfaces, so you can use it through JSR 107 if you're looking for a caching library. We also have CDI support, context and dependency injections. So it gives you a nicer interface for using Infinispan and importing it. Now let's look briefly at some of the key features Infinispan comes with. Infinispan can participate in transactions. Well, that would be. I'll talk more about it in the next slide. You can persist your data. You have the option to keep some data or to flush it on some persistent storage. Why would you want to do that? Because memory is limited and you might want to keep in the memory area only what's very relevant. Newspaper information from 1 year ago is not something user will access very frequently, so you can just keep it on the disk, but whatever was published today is what people will access, so just keep that in memory. It's limited and it's fast. MapReduce and querying in general, so this will be covered in the next few slides. Well, transactions first. Transactions are a very important aspect of Infinispan ecosystem, and there's a good reason for that. So Infinispan is primarily a data storage engine. Well, in the case of data storage or any data storage engine, you might have the question of data consistency, or more or less whatever ACID transactions offer you. And Infinispan is it's a highly consistent storage, and it offers support for JTA transactions, which implement the XA standard. So it can participate in distributed transactions in the sense that, from the book transaction example in which you move money from one account to the other, you can keep one account in Infinispan and another one in a database, and you can run a distributed transaction on top of the two resources. It also supports, well, recovery is an XA requirement, so we do support recovery as well. It has support for local transactions or batching. local transactions being used when you don't have, or when Infinispan is the only participant in the transaction. You just want an all or nothing batch operation. Well, the difference between local transaction and XA transaction is the fact that XA transaction would require a transaction manager, which is a bit more set up on your side. Local transactions are very easy to set up. You don't need a transaction manager. So if you just need transactions on top of Infinispan, not involving other data storage engines, you'll just use local transactions or batching. It offers two transactional modes, optimistic and pessimistic transactions. Pretty much depending on your data access and your application requirements. Optimistic transactions are a good fit when you don't expect concurrent writes to the same data. So you don't expect multiple users manipulating the same data at the same time, or it's just few times when this happens. On the other hand, pessimistic transactions are more suited when you have lots of users accessing the same data at the same time. They run, well, the difference is both of them would offer you transactional guarantees, but the throughput might be higher if you're using one or the other. So you have more transactions per second. Another very important feature we offer is persistent. One of the things we sell as an in-memory data grid is speed, and we gain speed by not accessing the disk, by keeping stuff in memory, so that whenever you write or read, you'll have very good and predictable speed. Where does the persistent kick in there? Well, if you need increased durability, if you just want to keep the data for years, you don't want to keep everything in memory, just what's very relevant. Again, for increased storage, same principle, just keep what's hot and what's being currently accessed in memory. Warm caches, when you use Infinispan as a caching engine, when you start it, it doesn't have anything in it. So you might want to just read some data from a storage and interact with the storage to make the cache very useful as it starts. By persistence, it's a very, in Infinispan's terms, it's a very abstract aspect. So we just have an interface, which is a cache store, and we have various implementations. Naturally, JDBC implementation, just to put, it's very easy to put Infinispan as a cache between an application and the database. Just plug in that JDBC implementation. BarclayDB as a file just on your local file system. In the cloud, we use JClouds to store, we can configure it to store Infinispan on whatever cloud engine you have. Remote, well, you can store your data in another Infinispan cluster, so you can build hierarchies of clusters if you so want. Cassandra, HBase in various NoSQL engines as well. And the good thing with it is that it's extensible. You can just extend this interface. It has 5 methods, read, well, some streaming reads for when the cache store is used as a for warming up the cache, so to read bulk data. So it's quite extensible. So just write whatever it fits your need and potentially contribute it back. It's open source. So actually, most of these implementations were written by Infinispan contributors. So just to give you a hint on how data can be manipulated with Infinispan versus a database, because if you think about it, the key value is quite limited. You have a key and a value, and how can you read it, and that's really not enough for many applications. You want a more semantically rich way of querying the grid. So this is how you insert stuff in a database, just 3 persons. And then you have a query through SQL to know how many persons are above 18. So select count from the person table. This is quite a semantically rich query compared with what a key value store offers, give me that value associated with it. So MapReduce is a good alternative for querying the grid. Basically, you write your query in Java, so you don't even need to write it in in specific language. You just receive objects. You need to be aware of the object you store. You iterate over all these objects, and you take actions based on this. You select the ones that are interesting for you, and you ignore the other ones. So the first part is this is how you'll insert data. We'll just use the it's an Infinispan cache. It extends Java util concurrent hash map. Then you add some objects, the same data as you did in the previous query, in the previous slide. And then it's the different part. You write a MapReduce task. This is the MapReduce that will, basically what happens, this task will be executed on all the nodes in the cluster. It will be serialized, sent across on all the nodes in the cluster. It will be run in parallel, which is quite nice because, you have a parallel structure, so no point in being sequential about it. And then data will be aggregated and sent back to the node on which the task was run. So you build a MapReduce task. You use a mapper, and we'll see how the mapper is used. And then a reducer. So the map and the reducer. And then when execute is being invoked, the task is serialized, sent across. And the result is being brought in the map, in the map, which is called their count. So this is the mapper and reducer. You have to implement two interfaces. Map, what the map will do, it will basically all the data on every node. We will iterate over all the data. We will feed it into the mapper. The mapper will choose whatever is relevant for it, and it will emit it into a collector. So that's basically a filter. That's a filter step. Just as a note, you can potentially iterate on the data that's in the store as well, not only what's in memory if you wish to do that. So first the mapper selects whatever is relevant. In this case, we look for the persons that are above 18, otherwise we just ignore them. And then you have the reducer, which will count these persons. So for each such person, we'll just increment it. And then what you'll get is the sum. It's a very simple example, but just to illustrate how you can write a more complex query. It's a way of querying MapReduce. Besides MapReduce, well, the thing with MapReduce is that if you just want, it doesn't allow you to index that much. So everything will be stored. And that's good if you want to go through all the data you have in the grid. But you don't always want to do that. So if you want something that, like in databases, like indexes, or want to just query for a specific subset of data, you'll want to use this kind of querying, which is Lucene-based. It will have an index. You'll have to take care of the index. So you can store it in a Lucene directory. We have an Infinispan Lucene directory implementation as well. I won't go into that many details, just to give you an idea. Basically, what you'll end up using is Lucene queries on the grid that will be run in the grid. And that's, again, a very powerful way of querying through Lucene. So again, you have key value stores in which you just query to key value. You have MapReduce and Lucene-based querying so that you can interact with the grid. Now the next section is about the use cases for Infinispan. 4 major use cases: a local cache, a cluster of caches, using Infinispan as an autonomous data store, like a database replacement. And there are various ways in which you can access this, and as we'll see. And there's a cluster of clusters, basically, in which you can have multiple You can use Infinispan for geographical failover. If a whole site goes down because of a catastrophic failover, and you still need to keep that data around, like if it's very sensitive data, like medical data, you'll just back it up to another store and use that store. The very simple use case, it's a local cache. You just have a client, you have a database. Reading data from the database is a costly operation. What you do is you read it, you put it in the cache, and then the next time you need the same data, you look in the cache. If it's in the cache, you'll just read it from there so that you don't go to the database and you get the performance. You get increased performance. It's a from the book pattern of local caching. Well, you can use, for that you can use a concurrent hash map or a hash map, but you don't really want to do that for several reasons. Infinispan and any other JSR 107 compliant caching library gives you eviction. That means you'll only keep in memory whatever is relevant, whatever is frequently used, or whatever was recently used. It gives you expiry so that you can say, keep this for the next 5 minutes, then just drop it off. I won't have to, as an application, take care of that logic. Right behind is, it simply allows you to interpose a cache between your application and the database without necessarily writing the SQL that reads from the database and writes into the cache. You just need to configure things. Preloading has to do with worm caches. Notifications, you can register listeners so that you know when the cache is started or things are being taken off the cache. And very important statistics. So you do want to know if your cache is successful. Things like, how many successful queries were done against that cache. Because if your application constantly asks about data and you'll never find it in the cache, there's no point using a cache. Statistic will tell you that if your cache is helpful or not. We expose them through JMX and quite some nice statistics. Okay, moving forward, local caches have limitations, and on the short, the biggest limitation being dirty reads. What's a dirty read? So you read the data from the database, you write it in the local cache. The next thing you do is you have another client writing or updating the data in the database, and the first clients read the data from the cache. It will read the stale value. There are applications that can live with this. There are applications that they can't live with this. They need to have the last data always, but they need caching as well for performance. So local caches won't help you here. But what you can do is just use a cluster of caches. So in this situation, you have two clients running in two independent processes, or JVMs, just to say that there are Java clients. So what happens is when the first client okay, so the basic idea is that when you write to the database, you also update the cache. And if you update the cache on one client, the data will be replicated and updated on the other client as well, so that when the next client will read the data from the cache, it is guaranteed to have the last value. This operation of updating both the cache and the database is a transaction, and it's a distributed transaction. So you have very high consistency guarantees there as well. This is basically the pattern that Hibernate second-level cache does, and it just does that for you. This is exactly what it does. It's just that between the two caches, it doesn't use replication. So when you update one cache, it doesn't copy the data to all the other nodes in the cluster. It will send an invalidation message, which will tell, OK, this node has the latest value. Whoever else has the value in the cache, just remove it because it's outdated, it's stale. There are limitations with local caches as well. With cluster of caches, with the clustering with the cluster of cache I've just showed in the previous slide. One limitation is the fact that clients are affected by topology changes, slightly affected. What I've said in the first slides, that topology changes won't affect the clients, was a bit of an overstatement, actually. Because what we do when a node leaves, we'll do some computation. We'll use some CPU and some network resources just to rebalance the whole cluster. We do that gradually and minimally, but there are still CPU cycles that you need to count to know that they are going to be taken from you. So again, shared resources will be used more, like sockets, so on and so forth. And your application might need all the resources it has available. On top of that, there are tire management concerns. For example, if you have a CPU-bounded application, because you do a lot of calculus, you might need to tune the JVM in a way which is very CPU-oriented. But your data storage would need to be tuned differently, like your garbage collection might need other tuning parameters if you use Infinispan as a storage engine in the same VM. Security concerns, you might have different security concerns. For example, there are requirements in which you cannot migrate your data where your clients are because of legal reasons, and that's another security concern. And well, I think most importantly, you might want to consume a data grid from a client that's not written in Java, or you might want to access it from Java and then some other application which is written in C to be able to access it as well, so that you physically cannot co-locate the client and the grid node, and by co-locate I mean place them in the same process. So in order to overcome these limitations, what you can do is use cache servers. In this situation, the client's processes live on a totally different place than the grid processes, all these squares being processes. So we have 3 clients, all of them living in their own process. They can be different clients, perhaps C++ or other clients. And then you have a grid living on a totally different layer, and perhaps your database. And you can still run transactions between the database and the grid, like whatever you read from the database, write to the grid transactionally, and still use it as a cache if you so want. Because reading from an in-memory storage or a remote network read, it's still about 1 order of magnitude faster than accessing quite a fast disk. So, this still offers you a very good balance between separating your concerns and allowing you also to use non-JVM clients and caching. The client server or the client server access can be done in several ways. Well, REST, you can start Infinispan and tell it, open a REST endpoint. That means that you can send HTTP requests as described by the REST protocol. You have whatever HTTP client you want to use for that. You can also put a load balancer, an HTTP load balancer on top of it so that you can balance requests between the Infinispan nodes. We have a memcached endpoint, so you can start Infinispan and it will run as a memcached server with clients written in virtually any programming language, memcached being quite popular as well. So you can use Infinispan for memcached. Why would you want to do that? Because you can, it gives you a higher degree of consistency to the data you write. You can guarantee the number of copies. And we also have our very own protocol, which is called Hot Rod. It's an open protocol. It's proprietary in the sense that it was designed especially for Infinispan, but it's an open specification. It's binary, so both REST and memcached are text protocols, so the size of the data or the meta information is quite high. Hot Rod is the payload is quite small. Some very nice features, like the client is always aware of the topology. So the topology information is piggybacked to the client. if you start a client with 3 nodes and at one point, you just grow the cluster and these nodes will disappear, the client will always be aware of the latest topology, and it knows how to balance requests between the existing nodes. Another nice feature is the fact that the client is aware or has the logic of knowing if a key is on the server side, on which node or on which server node the key is located. So instead of picking up a random node to go to ask for data, it will always go to the node that has the data. This way, reducing the number of round trips and being more efficient. We have several clients written, Java naturally, C#, Python, Ruby, and others on the way, most noticeably C++. There is high demand for C++ clients. So that's on the way. I think the last slide is on geographical failover. So Infinispan can be used for failing over between sites in case of a catastrophic failure. For example, you might have the same data or different data but backed up on different sites. For example, you have, as a bank, you might have a branch in Europe, one in US, on East and West Coast. And what you want to do is, if something terribly bad happens with one of your sites, just be able to migrate clients to other sites. Is not optimal for a client located in New York to access your server in New York, in London, but it's better, even if it's slower, it's still better to allow them to access it. So basically what happens is, if you write the data, you can configure it so the data that's written in London is being backed up in New York, and the one written in New York is being backed up in San Francisco, and so on and so forth. You can even say whatever written in London to be backed up in both other sites, but it's really up to your application requirements. This has been added recently in Infinispan 5.2, and it's quite a popular feature, actually. For either follow the sun, so to keep your data where your clients are, or that data proximity or geographical failover when a site goes down, to allow your users to still be connected to the cluster. Before I finish, I'd like to also mention that Infinispan is an open source project. You can just use it, start all the things and all the features I've discussed about. You can just start using them out of the box for free. But Red Hat also offers professional support for Infinispan. It's called the JBoss Data Grid, and you can find more information about it there. Thank you very much for your time. I think we still have 1 minute or so for questions, but I'll be around if you have any other questions. So, yes, please.
I have a question about the elastic capacity. I heard about Infinispan some months ago. So I wrote a very simple application that write and read property. And then I start many virtual machines on the same node. And they work together because the first write the property and the other can read the property. But when I use two different nodes and I start different virtual machine on each node, it doesn't work.
Two different physical machines.
Yes, two different physical machines. And I read about this problem, and on many posts they said that I have to use the two Java properties to add on each machine. The first is the EP machine, the EP machine on where I start the first Java virtual machine, and then the list on each other nodes.
Right.
but and this works. Okay, but if I want to start a lot
of machines, you don't want to be statically configured. Right. So the nodes will discover that when you start an Infinispan cluster, you'll have to make the nodes see each other. In order to do that, you can either statically define each node to each node to see all the other, but that's not nice because if you have 1,000 nodes, it wouldn't work. What you can do is use UDP for that. We have a UDP-based discovery mechanism, and they will just multicast their address. And yes, it's called UDP discovery. Yes, if you Google JGroups UDP discovery, you'll find that. Okay. Well, I think the time is done. But if you have any more questions, I'll be around.
Codemotion.